So when you see this question, it looks like an equation, but then you quickly realize this is actually a functional equation. So it's hard to do the normal sort of equation things. Like we can't really factorize out an f of n here. This is actually a composite function. It's not f of n squared. And yeah, we can't do things like that. So immediately what I thought about doing was, well, let's think about polynomials because for most other functions, think about exponentials, think about, things like floors. I mean, that floor is a bad example, but for most of them, they don't deal with integers, they rather deal with the real numbers. So logs, exponentials, sines, trigonometric functions, they all deal with real numbers rather than integers. And so we're left with things like floors. We won't be going into those functions now. But my solution is really going to focus on the polynomials because I figured not no other function is going to be able to produce only integers when it's composite, and then on top of that, it needs to be equivalent to that when it's not composed on top of itself. So there might be some other examples out there, but for me, I was just going to focus on the polynomials. Once we narrow it down to the polynomials, we can actually, our life becomes a bit easier because you'll see the left side actually has itself composed, if that's a verb. So if we had something like a quadratic, when you put a quadratic inside of a quadratic, let's define f of x to be this quadratic. Then if we put f of x inside of itself, we're going to end up with, well, we'll have something squared, and inside of this we'll have x plus x squared plus x squared plus x. And so you'll notice this term is going to expand to give us a quintic term. And for any higher order polynomial, it's going to give even larger degrees because if we had a cube there, this would be cubed, this would be cubed, so we end up with an x to the 9 term. So our degree effectively gets squared when we compose the function, which means we can't really have it being, if our degree is squared on this side, it should also be squared on this side, but that's not going to happen. So if we have a quadratic, this side would be a degree 4, whereas this side would only be a degree 2, and so they obviously couldn't be equivalent for all n. So with that out the way, that means the only way to match the degrees on both sides would be to either have a constant function, so we could either have f of n is equal to a constant, and we'll just call it k. In that case, the left side would be a degree, I guess it'd be degree 0, and the right side would also be, well, the right side would be a degree 1, right? Because this still has an n term in it. So again, this could never work. Even a constant function wouldn't work, the degrees don't match. Which means we're ultimately left with a linear function. So if we had a linear function, notice if we had f of n is equal to an plus b, when we compose this into itself, we actually end up with another linear function, which means putting a linear function into this equation, our degrees would match, so this could be a possible fit. And so we managed to narrow it down from all possible functions to only linear functions over here. So that's good. Now we just have to use our linear function general solution, I guess, and plug it into this and then solve for a and b. So let's do that here. In the left side, we're going to get 2, and then let's just use what we already have here. So you have 2a an plus b, and that's going to be equal to 5 f of n, which is an plus b minus 2n. Okay, now remember this is true for all n, so this is actually an equivalence. What we can do then is expand everything out to get 2a squared n plus 2ab plus b. That's equivalent to, and then I'm going to expand out this 5an and factorize it with this minus 2 to get 5a minus 2n plus 5b. And see, because this is an equivalence, we can now match coefficients. So therefore, 2a squared is equal to 5a minus 2. Since the left and right side are both the exact same function, they have to have the exact same coefficients. That's the only way they're going to be true for all n. So here's our first equation. nice equation in A, and then we have a second equation, 2ab plus b is equal to 5b. So there's the second equation. Now we can solve this first equation just in A, so we get 2a squared minus 5a plus 2 is equal to 0. Factorize that to become, let's see, 2, 1, 1, 1. So that's going to become 2a minus 1 and a minus 1 is equal to 0. And that tells us that a is either equal to a half or 2. Okay, that's good. So now you'll notice if a was a half, our function would look like this, and if a was 2, our function, we'll call this b1 and b2, our function would look like this. Okay, now it's important to read the original question here. So notice how it says from integers to integers. So no matter what b1 is, even if this was some fraction, if a was a half, then there would always be numbers which we could put into n to make this return a non-integer. For example, if we put f of 1 in, that would give 1 half plus whatever b1 is. And if b1 happened to be a half, well then, if we put in something like 2, this would become 1. So now this is now also not a integer. So clearly, when when a is a half, there aren't any valid solutions from integers to integers. So this means we can effectively reject a half. Okay, there we go. So now we have a singular solution, a is equal to 2. What we can do is simply plug this into equation number 2 to get 2 times 2b plus b is equal to 5b. And you will notice 5b equals 5b, which yields b equals b. And essentially, well, this doesn't really tell us anything, does it? Doesn't tell us anything about b. We must have made some error somewhere. Let's have a look. Everything seems to be all fine, all good, all good. Oh yeah, this should be a 2 there. Okay, so now let's try this again. 2a plus 2b is equal to 5b. Bringing this down, so we have a 2 over here as well. Okay, so now this tells us 6b is equal to 5b. Alright, there we go. That's better. So now either b is equal to 0 or 6 is equal to 5, but 6 is not equal to 5, therefore b is 0. So that tells us overall our function is going to be f of 2n, and that's the only solution, especially in the polynomials. Now, if someone in the comments would like to make a more convincing argument why we can ignore all other functions, that would be great. But I think the idea that all other functions can't really map integers to integers is all right. It's not rigorous at all, but it is. It does make intuitive sense, and yeah, I really can't think of any other example of a function which isn't a polynomial, or which isn't a linear polynomial that will be equivalent on both sides, especially after a composition. Unless it was something which was reversible, like 1 over x, but even then, it doesn't seem to work. So yeah, if someone in the comments would like to make a better explanation, that would be nice. But for now, the only solution is f of n is equal to 2n. Thanks for watching, and I'll see you guys in a future tutorial. Bye!